Welcome to an example on how to solve a rational inequality. Looking at a rational inequality, notice how it looks different than the previous examples because it's not in the form of a rational expression being compared to 0. But it needs to be in this form, so for the first step, we're going to go ahead and add 2 to both sides of this inequality. So that would give us the quantity x plus 5 divided by the quantity x plus 2. And if we add 2 to both sides, we'd have plus 2 over 1. I'm writing this in fraction form because we will have to add these fractions. And now it would be greater than 0. To add these fractions, our common denominator would be x plus 2. So now we'll multiply 2 over 1 by x plus 2 over x plus 2. And now that we have a common denominator of x plus 2, the numerator would be the quantity x plus 5 plus 2 times the quantity x plus 2. This is still greater than 0. And now we'll simplify the numerator. Notice if we distribute, we would have 2x plus 4. So now we would have the quantity x plus 2 as our denominator. The numerator would now be x plus 2x, that's 3x, and then 5 plus 4, that'd be plus 9, greater than 0. And now we're going to go ahead and factor the numerator and denominator if we can. Notice how the numerator does factor. There's a common factor of 3. So we have 3 times the quantity x plus 3 divided by the quantity x plus 2 is greater than 0. And now we're going to determine the zeros of the numerator and the zeros of the denominator. So the zeros of the numerator would occur when 3 times the quantity x plus 3 equals 0. Well, this would be 0 when x equals negative 3. The zero of the denominator would be when the quantity x plus 2 equals 0, which is when x equals negative 2. So now we're going to plot these values on the number line to determine our intervals, which will then test to determine the solution. But when plotting the values on the number line, the zeros of the numerator will be either open points or closed points based upon the original inequality symbol. Notice here we have a greater than symbol, which means we'll make an open point at x equals negative 3. If this was greater than or equal to, then we would actually make a closed point at negative 3. But the zeros of the denominator will always be open points because these are the values where we would have division by 0, and therefore these values must always be excluded from the solution. So again, if we sketch a number line to form the intervals, let's say this is 0. The 0 of negative 3, again, is going to be an open point because of the original inequality symbol. And then negative 2 is going to be an open point because it must be excluded, otherwise we'd have division by 0. So notice how we have 3 intervals to test: to the left of negative 3, between negative 3 and negative 2, and to the right of negative 2. Let's go ahead and do the testing on the next slide. And to test, we are going to use the factored form of the rational inequality when we're comparing it to 0. So to the left of negative 3, let's test x equals negative 4. Between negative 2 and negative 3, let's test x equals negative 2.5. And to the right of negative 2, let's test x equals 0. Because we're comparing this to 0, we really only care about the sign of this rational expression for these given values of x. So notice when x is negative 4, we would have 3 times negative 1 divided by negative 2. That's going to be positive, which is greater than 0, which is true, which means the interval to the left of negative 3 would be part of our solution. And now let's test x equals negative 2.5. If x is negative 2.5, we would have 3 times 1/2, or 0.5, divided by, this would be negative 0.5. Well, this would be negative, and therefore it's not going to be greater than 0, and therefore this would be false. This interval here is not part of the solution. And now we'll test x equals 0. Well, if x is 0, we would just have 3 times 3 divided by 2, which is positive, which is greater than 0, and therefore that's true. And therefore the interval to the right of negative 2 would also be part of the solution. So this would be the graph of our solution. If we wanted to use interval notation, we'd approach negative infinity to the left, positive infinity to the right, and therefore using interval notation, this would be the open interval from negative infinity to negative 3 union the open interval from negative 2 to positive infinity. Or if we wanted to use inequalities, we could say when x is less than negative 3 or when x is greater than negative 2. Before we go, I do want to show how we can check this using a graphing calculator. Remember, our first step was to add 2 to both sides of the inequality so we can compare the result to 0. So if we left it in this form here and then graphed y equals this quotient plus 2, this would be the same as determining when y would be greater than 0. Y is greater than 0 when the graph is above the x-axis. And because of the inequality symbol, we would not include the pointer points on the x-axis. So looking at the graph, notice how we would not include this point here on the x-axis, but then to the left of negative 3, notice how the graph is above the x-axis, meaning y is greater than 0. Verifying the interval from negative infinity to negative 3 would be part of our solution. Then looking at this piece here, notice how we have a vertical asymptote at x equals negative 2. But more importantly, notice how the graph is above the x-axis when y is greater than negative 2. So this would be an open point, and then to the right. Notice how this interval graphed on the x-axis is the same interval we found on the previous slide as we see here. I hope you found this helpful.